This video is about finding eigenvalues using TI-AD4. I start with an example. Let's say I'm trying to find the eigenvalues of matrix given over here. First step, as usual, go to the matrix environment. Edit the matrix. It should be 3 by 3, 0, 1, 1, 1, 0, 1, 1, 1, and 0. Then quit the matrix environment. Go back to the top part where you can graph. Press y equal to. Clear the functions that you have. While over there, without quitting, go back to matrix environment. And this time use DET, determinant, the first entry in math column. So this is the first entry in the math column. Press enter. So in front of y1 you see a determinant. Then go back to the matrix that you have. So back to a matrix environment without quitting. Choose the matrix that you just entered. Then subtract x times back to the matrix environment, back to math column, go to identity matrix, press identity, and here we have to enter a number. The matrix that we entered over here is 3 by 3. So here we have to enter a 3. Now it's the graphing time. And then you find there are two values that make the function equal to 0. What I can do is I can use the calculator button up there using second and trace and find the zeros. So one of them has to be the coming from the left bound here, right bound there, enter, and it gives me x equal to 2. And then the other one is again 0. This time left bound over here because I can see a 0 down there. Right bound is here. And it's calculating 0 x equal to -1. Now, why are we interested in where the graph of the function? This was the function that we graphed. Determinant of a minus x times identity. And now we're finding what value of x makes that 0. If you notice, this is how we find eigenvalues. We set the determinant of a minus lambda I equal to 0, and we find what lambda makes that happen. So basically, what we entered, determinant a minus lambda I, is a polynomial of degree 3 in this case, because a is 3 by 3, and the zeros of that polynomials will give me the eigenvalues of the function, of the matrix, I'm sorry. Now, looking at this, I need to figure out two things. First of all, this one, the 0 over here, the function goes through, and it's not tangent to x-axis. Therefore, x equal to -1 is of multiplicity 1. Multiplicity equal to 1. But x equal to 2 is of multiplicity 1. That's x equal to 2. X equal to -1, I see that the function, the graph of the determinant of the polynomial function is tangent to x-axis at x equal to -1. That means that multiplicity is more than 1. Since I have one solution of multiplicity 1 and the polynomial is of degree 3, what is left is of degree 2. So this has to be only of degree 2. So multiplicity of this one is 2. Now, we can use this material that we already have to figure out, to solve for the eigenvectors. One quick way of doing this, and I will not complete it, but I will show you how to find the reduced row echelon form of A minus lambda I quickly on your calculator. Because you already have entered A, what you want to do is you go back to the matrix environment, to math environment, use the reduced row echelon form, enter matrix A, and for example, for this one, I enter 2, then I enter back to math environment, identity 3, and it gives me the value for x equal to 2, the reduced row echelon form of A minus lambda I is going to be 1, 0, -1, 0, 1, which will give me a null space of dimension 1. I could do the same thing. Instead of 2, I can enter -1, which makes this positive 1. And then I get the reduced row echelon form of A minus lambda I for lambda equal to -1 is 1, 1, 1, 0, 0, 0, 0, 0, 0, which is the null spaces of dimension 2. Continuing the example that we started with our calculator, this was the matrix. We found two eigenvalues. First one of multiplicity 1, second one multiplicity 2. Now we found the reduced row echelon form of A minus 2i and reduced row echelon form of A minus minus 1i. From here, to find the eigenvectors associated with 2, I have to rewrite the system. x1 plus negative x3 equal to 0, and then 0, x2 minus x3 equal to 0. And as we're expecting, this is supposed to be, we're finding the null space, therefore there should be rows of zeros on the bottom. In this case, the only column that doesn't have a leading 1 is x3. Therefore, I assign x3 equal to t, put it back into here, x2 is equal to t also, put it back into here, x1 equal to t. Therefore, t gives me t times 1, 1, 1. So a basis for this new space, for this eigenspace, is 1, 1, 1. Now, for the second one, I again have to rewrite the system. This time, there are two variables without needing one. Set x3 to be t, x2 to be s. Now plug it back into here, and we get x1 is equal to negative t minus s. Rewrite the solution, negative t minus s, s and t. Separate them. Separate the variables, negative t, 0, t, plus negative s, s, 0. Factor out the parameter, negative 1, 0, 1, negative 1, 1, 0. These two vectors are, they make a basis for the eigenspace here. So eigenspace is span by this basis. And we're done with this example. Next comes a few examples of just finding eigenvalues for 2 by 2 matrices.